Okay, we're going to talk about horizontal asymptotes, aka M behaviors. And what we're going to do is we're going to determine the limits are infinity of a function if they exist, describe the M behavior, and compare the magnitudes of the function. All right, so here we go. When you're trying to find N behaviors or horizontal asymptotes, in reality what we're finding are limits that approach infinity. And so when we have this right here, we need to compare the growth rates of the numerator and denominator. So whenever you want to find a limit to infinity of a function, generally this function is going to be a rational function. And so you have a numerator and you have a denominator. Okay? Now, when you want to find these horizontal asymptotes, you have to compare the growth rates of each one of these functions. And so what happens is when you look at growth rates of functions, you need to compare what type of function they are. So if you have right here, you can see on my slide, I have like a little chart of the hierarchy of growth rates. So exponentials, all right, well, I probably would say factorials, all right, factorial functions, which look like this, all right, factorials, grow the fastest, okay? So these are grow the fastest. Okay, then followed by exponentials, and this would be like a to the x, followed by power functions, which are x to the n, then logarithmic functions, which are the snails of the bunch, which are natural log of x, or, all right, log base b of x, and then you have cosine or sine function, like a trait function, cosine or sine of x. So when you compare these, what we know is that if you notice the numerator happens to be one of the functions that grows the fastest, that means the fraction is growing without bound. Okay, it's growing without bound, and we would say that limit diverges, the limit does not exist. If you know that the denominator grows faster than the numerator, we would then know that the fraction is becoming smaller and smaller as x goes to infinity or negative infinity, and therefore it's approaching 0. And then finally, if the growth rate of a function have the same growth rate as the numerator and denominator, then we know that it's going to be equal, and we're going to do leading coefficients. And so right here, we have a little example called example number 1. Well, if we compare this, we're taking a limit to infinity. Which one's growing the fastest? Well, the numerator, all right, is sine. Well, sine and x, which is a power function right here, the power function, the denominator, grows faster than the numerator, and because the numerator grows faster than the denominator, we would know this is approaching 0. All right, let's try some just to kind of figure this out. All right, so here we go. In order to do this, we're going to find the following limits. We're going to take the limits going to infinity. Okay, so these limits right here, when we're taking this. Now, you can see that we have x squared minus 5, 2x squared plus 1. Now, one thing we can do to solve this, all right, is you notice that we're going to compare the growth rates in the numerator and denominator. Well, both of these are quadratics. So the numerator is a quadratic, the denominator is a quadratic, and so we would say that these are equal in growth rate. Now, just to show you how this works, all right, and why it works, why we're going to use the leading coefficients, I'm actually going to multiply this by 1 over the highest power, the highest degree. And I'm going to multiply both top and bottom by that. When we do that, we can multiply this through. And what we have then is when we take the limit as x goes to infinity, oops, not like that, as it goes to infinity, all right, is we're going to have 1 minus 5 over x squared. And then we have over here, we have 2 plus 1 over x squared. And when we take this to infinity, well, 1 is going to be remain 1. 5 over x squared, well, that approaches 0 because the denominator grows faster than the numerator, so it's going to be minus 0. Over 2 plus 1 over going to infinity, where it's going to equal 0. And so we have is 1/2. And that's why whenever the numerator equals the denominator in degree or in growth rate, it's going to equal the leading coefficients. I'm just going back to my other slide, and that's why you see right here, all right, when the growth rates are equal, the limit is going to equal the leading coefficients. All right, let's continue on. So for example, this one, example number B, we compare the numerator and denominator. Well, the numerator is 100. The denominator is x squared. Which one grows faster? The denominator does. The growth of the denominator is faster. Therefore, we know this is getting smaller and smaller as x goes to infinity, and so it's going to equal 0. We can continue on, and the same thing applies when we go to negative infinity. When we look at this right here, we compare the numerator and denominator. The numerator in this case is x cubed. This one is x squared. The numerator grows faster, and if we go back to our chart, if the numerator grows faster than the denominator, that means our fraction is going to keep on growing, and therefore our limit does not exist. It has no horizontal asymptote. The behavior here approaches, in this case, it's going to approach negative infinity. All right, and that's what we got there. And it doesn't matter if you go infinity or negative infinity. In each one of these cases, this is going to go to numerator is still greater than the denominator, except in this case, so that does not exist. But because it's going to positive infinity, positive or positive makes it positive infinity that it's approaching, which is not a limit. All right, you can try these two. These are a little bit more difficult, okay? But in doing this, we're going to take the limit to infinity and negative infinity. Normally, these are the same unless we have an absolute value, all right? But when we look at this, okay, we're going to have the cosine. And so the first thing is I'm going to simplify this into a fraction because we see we have x cubed, we have cosine squared. So I'm actually going to rewrite this. And I'm going to rewrite this as cosine of x over x cubed minus 2x cubed over cosine cubed. And I'm going to take the limit as x approaches infinity. All right. And now when we look at this, I'm going to do the first one. So I'm going to do each one individually. The first one, we have cosine of x over x cubed, which we know the numerator grows slower than the denominator. So that's going to be approaching 0. Over here, we can see the numerator is equal to the denominator in growth rate because both of these are cubes. So it's going to lead the leading coefficient. It's going to be minus 2 over 1 because it's 2 and this is a 1 there. And so 0 minus 2 is 2. And that is going to be the same for both infinity and if we approach negative infinity. So this one's going to equal 2. And this is also going to equal 2. Doing the same thing over here, we can start with the limit as x approaches negative infinity. I'll start with that one here. All right. Same thing, we have 2. Well, 2 minus x over x plus 1 times x squared over 5 plus x squared. Going through here, what's happening to 2? Well, 2 is going to be 2. We have x over x plus 1. We notice that the numerator and denominator are equal in growth rate because they both have 1. Therefore, it's going to be the leading coefficients, which is 1 and 1. So 1 over 1 is 1. Looking at this one, we see we have, all right, 2 and 2 x squared. It's going to be leading coefficient, which is 1 and 1. And so once again, the same thing. So I'm going to have that one's going to equal 1 as x goes to negative infinity. And so now what do we have? Well, 2 minus 1 is 1 times 1. Our value is approaching 1. 1 from negative infinity. And guess what? If we went to positive infinity here, it would go to the same place because there is really no difference unless the bounds change when we're doing it. And that's what we got. All right, we're going to start with another section right here. What's happening as we approach these limits of infinity for this function f of x. So the limit as x approaches negative infinity for f of x. Let's check this out. Well, I'm approaching negative infinity. Now, this is a piecewise graph. So what am I looking at? So for this problem, as we approach negative infinity, I'm looking at the values. It's going to be negative. Well, these are all negative values. So I'm going to use this graph, 1 over x. And what that's going to do is I compare the numerator and denominator. The denominator is greater than the numerator, so this is going to be approaching 0. Same thing if I take the limit as x approaches infinity. Well, x is greater than that, so it's going to equal negative 1. So what's the limit as x approaches infinity for -1? That's going to equal -1, because that's constant horizontal line. When we look over here, what's happening as we approach the limit? As x approaches 0 to the right, that means we're getting values that are just to the right of 0. That's going to equal -1 is the function I'm using, because I'm approaching all values that are greater than 0 from that side, greater than 0. So it's going to be all x values greater than that. And so that's going to be using function -1. Well, as I approach, plug those values in, it's going to equal -1. In the same way, as I approach the limit, as x approaches 0 to the left, I'm using this function. It's going to have 1 over x, but as I plug in values getting closer to 0, I realize that this equals 0, so this one does not exist, and actually is like a vertical asymptote. And so when I plug it over here, this appears to be approaching negative infinity, because when I plug in a value, I'm plugging in like -0.1 in there, or 0.001, but they're both negative, so 1 over a negative equals negative infinity. All right. Well, I hope this helps you out in understanding about these limits. All right, specifically with horizontal asymptotes, because limits to infinity are in fact how you find horizontal asymptotes. Just to finish up, we found limits to infinity. That's how we have it, and we can write the horizontal asymptote as y equals 0. All right, and that's what we do there in finding for all these different ones. Okay, well, I hope this helps you out in finding limits to infinity, when x goes to infinity or negative infinity. And yeah, good luck and God bless in the rest of your problems.